Hello, today we're going to dive into one of the most fundamental and useful equations in fluid mechanics, the Bernoulli equation. By the end of this video, you will be able to understand the physical meaning of each term in the Bernoulli equation, apply it to solve practical problems, and understand its key assumptions and limitations. Think of it as a special form of the conservation of energy principle, but tailored specifically for fluids. It tells us that in a steady, non-viscous, incompressible flow, the total energy per unit volume of the fluid remains constant along a streamline. Let's write down the equation. It looks like this. P plus 1/2 rho v squared plus rho gz equals a constant. This equation might look a bit intimidating at first, but it's actually quite intuitive once we break it down. Each term represents a different form of energy that the fluid possesses. Let's go through them one by one to understand their physical significance. First up is the term P. This is the static pressure of the fluid. It's the pressure you would measure if you were moving along with the fluid. You can think of it as the potential energy stored in the fluid due to its compression. It's the work done per unit volume to push the fluid into a system. So, it represents the pressure energy of the fluid. Next, we have the term 1/2 rho v squared. This should look familiar. It's the classic formula for kinetic energy, but expressed per unit volume. Here, rho is the fluid's density and v is its velocity. This term represents the kinetic energy of the fluid due to its motion. Finally, we have the term rho gz. This is the potential energy of the fluid due to its elevation. Rho is density, g is the acceleration due to gravity, and z is the height of the fluid above a reference point. This term represents the potential energy of the fluid due to its position. So, to recap, the Bernoulli equation states that the sum of pressure energy, kinetic energy, and potential energy per unit volume is constant along a streamline. It's a powerful statement about energy conservation in fluids. Now that we understand the terms, let's see how to apply the Bernoulli equation. The most common way to use it is to compare the energy at two different points in a fluid flow. We can write the equation like this. P plus 1/2 HOV1 squared plus RHOG-Z1 equals P2 plus 1/2 RHOV2 squared plus RHOG-Z2. This equation says that the total energy at point 1 is equal to the total energy at point 2. This allows us to solve for an unknown variable at one point if we know all the variables at another point. Let's work through a classic example, the Venturi effect. Imagine a pipe that narrows down. We'll call the wider section point 1 and the narrower section point 2. Let's assume the pipe is horizontal, so the elevation z is the same at both points. This means the RHOGZ terms cancel out. Our simplified equation becomes P1 plus 1/2 RHOV1 squared equals P2 plus 1/2 rho V2 squared. Now, think about the principle of conservation of mass. For an incompressible fluid, the volume flow rate must be constant. This means the velocity must increase in the narrower section. So V2 is greater than V1. For the equation to hold true, if the kinetic energy term on the right side increases, the pressure energy term P2 must decrease. This is the Venturi effect. Pressure drops in a constricted flow. This principle is used in carburetors, flow meters, and even in the design of aircraft wings to generate lift. It's a direct consequence of energy conservation. Let's try a numerical example to solidify this. Suppose we have water flowing through a horizontal pipe. At point 1, the pipe has a diameter of 10 centimeters. The pressure is 200 kilopascals, and the velocity is 2 meters per second. At point 2, the pipe narrows to a diameter of 5 centimeters. We want to find the pressure at this point. First, we need to find the velocity at point 2. We can use the continuity equation, which is based on conservation of mass. The continuity equation states that the area times velocity is constant. So A1 V1 equals A2 V2. The area of a circle is PER squared, or pi d squared over 4. Plugging in our values, we find that the velocity at point 2 is 8 meters per second. As expected, the velocity increased in the narrower section. Now we can use our simplified Bernoulli equation. We have P1, V1, and V2. We know the density of water, rho, is 1,000 kilograms per cubic meter. We can rearrange the equation to solve for P2. Plugging in the numbers, we get P2 equals 200,000 pascals plus 1/2 times 1,000 times the quantity 2 squared minus 8 squared. This gives us a pressure of 170,000 pascals, or 170 kilopascals. Notice that the pressure dropped from 200 kPa to 170 kPa, which confirms the Venturi effect we discussed earlier. This example shows the power of combining the continuity and Bernoulli equations to solve for unknown variables in a fluid system. Now, let's talk about the assumptions and limitations of the Bernoulli equation. It's a powerful tool, but it's based on an idealized fluid. First, the flow must be steady. This means the fluid properties at any point in space do not change over time. Think of a river flowing smoothly, not a turbulent, churning waterfall. Second, the fluid must be incompressible. This means its density, ρ, remains constant. This is a very good assumption for liquids like water, but not for gases like air, especially at high speeds. Third, the fluid must be non-viscous. Viscosity is a measure of a fluid's resistance to flow, or its stickiness. A non-viscous fluid has no internal friction. This is an idealization, as all real fluids have some viscosity. Fourth, there must be no energy losses due to friction. This is a direct consequence of the non-viscous assumption. In a real pipe, the fluid rubbing against the walls creates friction, which converts some of the fluid's mechanical energy into heat. So, the Bernoulli equation gives us a perfect theoretical answer. In many real-world applications, especially in long pipes, these energy losses due to friction can be significant and cannot be ignored. This brings us to our next topic: how to account for these real-world energy losses. We do this by introducing a term called head loss. Head loss, denoted as HL, represents the energy lost per unit weight of fluid due to friction and other factors like pipe fittings. It's typically measured in units of length, like meters or feet. We can modify the Bernoulli equation to include this head loss. The principle is that the energy at point 1 must equal the energy at point 2 plus any energy that was lost between the 2 points. So, our new equation becomes P1 over ROG plus V1 squared over 2G plus Z1 equals P2 over ROG plus V2 squared over 2G plus Z2 plus the head loss HI. Notice that I've divided the entire equation by ρg. This converts each term into units of length, or head. So we have pressure head, velocity head, and elevation head. This form is often called the energy equation. The most common way to calculate head loss in a pipe is using the Darcy-Weisbach equation. The Darcy-Weisbach equation is HL equals F times L over D times V squared over 2G. Let's break this down. F is the friction factor, a dimensionless number that depends on the pipe's roughness and the flow's characteristics. L is the length of the pipe, and D is its diameter. The term V squared over 2G is the velocity head, which we've already seen. This equation tells us that head loss increases with the length of the pipe and the square of the velocity, and decreases with the pipe's diameter. It's a practical way to quantify the energy lost due to friction. Let's work through an example to see how to use the Darcy-Weisbach equation to calculate head loss. Suppose we have water flowing at 2 meters per second through a 100-meter-long pipe with a diameter of 5 centimeters. Let's assume the friction factor, F, is 0.02. Our goal is to find the head loss, HL, using the Darcy-Weisbach equation. The equation is HEL equals F times L over D times V squared over 2G. Now we just need to plug in our values. We have 0.02 for F, 100 meters for L, 0.05 meters for D, 2 meters per second for V, and 9.81 meters per second squared for G. Let's calculate this step by step. First, 100 divided by 0.05 is 2,000. Second, 2 squared is 4, and 2 times 9.81 is 19.62. So 4 divided by 19.62 is approximately 0.2039. Multiplying these together, we get a head loss of 8.156 meters. This means that over the 100-meter length of the pipe, the fluid loses 8.156 meters of head due to friction. This head loss represents the energy that has been converted into heat. If we were to apply the full energy equation, we would subtract this 8.156 meters from the total head at point 1 to find the total head at point 2. Let's quickly recap what we've learned today. We started with the Bernoulli equation, which is a statement of energy conservation for an ideal fluid. We broke it down into its 3 main terms: pressure energy, kinetic energy, and potential energy. We saw how to apply it between 2 points in a flow, and we worked through an example of the Venturi effect, where pressure drops as velocity increases. We then discussed the key assumptions of the Bernoulli equation, such as steady, incompressible, and non-viscous flow, and the limitation of ignoring energy losses. Finally, we learned how to account for these losses by adding a head loss term to the energy equation and how to calculate it using the Darcy-Weisbach equation. The Bernoulli equation is a cornerstone of fluid mechanics. While its ideal assumptions are important to remember, it provides a powerful and intuitive framework for understanding fluid behavior. By adding the concept of head loss, we can extend its utility to analyze real-world systems with remarkable accuracy. Thank you for watching.